We talk about chapter 6. We start out by talking about vectors. Vectors, you know what a vector is? Like an arrow. If you ever sit next to a physics type and they're doodling, giving ideas, talking about things, usually they put a whole lot of arrows to represent things. An arrow is a vector which represents like which way and how much. You know, like when we talk about flying into the wind. Notice in the textbook we talk about the airplane flying into the wind, and we can let the speed of the airplane, maybe the airplane's going due north, something like this, okay? We could let that arrow be the speed. Maybe it's 100 kilometers per hour, so I'd make it 100 units long. And let's suppose I'm going into a headwind, and the wind's coming toward me at 20. Well, I can go like this, see? Make an arrow 20. And when I combine these things, my ground speed's going to be what? This, take away this, so it's going to be that much shorter. Sort of like that, you know. And if you're going again, and this time the wind's coming behind you, a tailwind, and you're going again 100 with respect to the still area, and then if you got, say, a 20 coming behind you, those two things combine to be what? You're going faster. Do you need vectors to explain this idea? That if the wind's behind you, you go faster. If the wind's in front of you, you go slower. Answer begins with an N. No, you don't be needing vectors. But I'll tell you where the vectors do come in handy. Like you got a crosswind, okay? Let's suppose you're flying like this. And let's suppose the wind is a crosswind coming like this, just as fast as you're going. Let's suppose you're going 100 kilometers per hour, and you're in a hurricane, and the hurricane's coming like this at 100 kilometers per hour. What's the direction of the aircraft going to be? It's kind of easy to see, isn't it? Huh? It's kind of going like this, it's kind of going like this at the same time, right? And so what it does is it kind of goes off course like this, huh? Let me give you a neat little rule. We'll tell you exactly which way and how fast it goes. And the little rule is this. Take your two vectors, one representing ground speed, or the speed through the air, huh? And the other representing the speed of the wind, and make those into a parallelogram. Since they're at right angles here, that parallelogram is going to be, in this case, a square, because the sides are equal. Make a square. And then what you do is you join from here to the diagonal, and you make a vector like that. And guess what, gang? Guess what? That's the direction that the aircraft will travel. And furthermore, it tells you how fast it's going to travel. Because if this is 100, and this is 100, and that's a 45-degree angle, and it would be for both 100, yeah? It turns out, so this will be the square root of 2 times 100. Something like 140. So you'd be going something like 140 kilometers per hour that way. Isn't that kind of neat? Let's suppose instead the wind weren't so strong. Let's suppose you're traveling like this, and you got a crosswind about like that. Now, at your seats there, you guys taking notes, yeah? At your seats, draw this, and what I'm going to do in a minute, I'm going to go ahead and draw the solution, and you guys are going to look. But why don't you beat me to it? Why don't you draw what I'm going to do next to show sort of this thing here, but the angle's different, yeah? Why don't you do it before I do it? Go. Which is to say, you'll make a little rectangle, yeah? See how now this is a rectangle? And what's the diagonal of that rectangle represent, gang?
The direction.
That's right. Now you'll be blown off course only that much. And you know what? If you had a ruler and you did this to scale, you could measure that compared to this, and you could tell how fast you're going to go. Because the velocities will add together in that vector way. Really kind of neat. Any questions about that? So when we talk about how fast things go and we talk about velocity, we're really talking about direction too, yeah? And so we can represent that direction with an arrow. You know, I take this bowling ball and I roll it across the table. Okay. As it rolls across, let's suppose I took strobe pictures. One here, one here, one here, one here. Equally spaced times. You know what? I'd find equal spaced times would give equal spaces of distance. Do you know why? Because the ball's rolling at constant velocity. I mean, it's rolling here, then here, then here, then here. So my little velocity vector would simply be like this. I'm trying to draw that so all these are the same. Why? It's got the same speed along. See? It goes at uniform velocity, see? It takes a little push to get it going, but once I get it going, I let go. It kind of rolls of itself. And it rolls steady, 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 okay? And so these little vectors would just show me that it's rolling at constant velocity. Let's suppose instead I take it and I drop it. What's going to be now? Here it is up here, say. Then I drop it, it goes to here, then to here, then to here, and maybe down in here. Now up here, no velocity. But over here, a little bit. And over here, a little bit more. And you know the velocity is increasing because it's accelerating. Remember we talked about acceleration? And when the acceleration is due to gravity, we just called it g. Remember that? And we know that g for the planet Earth is, check your neighbor. What's the numerical value of g for the planet Earth? Check your neighbor. Don't say 9.8, let's round it off. What's it going to be? Begin with a T. 10, okay? Right? It's going to be 10 meters per second every second, right? That'd be acceleration due to gravity. And because it's accelerating, it's going to keep going faster and faster, true? That's why I make the arrow a little bigger here. It's faster here than here. And over here, I make it like this, even more. And that's because the speed picks up according to the acceleration and time. And the longer the time, the faster you're going. But you know that anyway. And so this is the relationship we talked about last time. How fast something goes depends upon how much it's accelerating and how long a time it's doing that. Isn't that true? Let's do a review. If I took this thing and held it up in the air and let it go, at the end of 1 second, what would its speed be? 10 meters per second, see? Because it started at 0. It's going to pick up to 10, okay? Let's suppose another second goes by. How fast is it going to be going? 20. Let's suppose 10 seconds go by. It's 100, see? Because every second goes by, it's going to be going 10 meters per second faster than the second before. To be sure you understand that, let's talk about this. Let's suppose you're downtown, you're looking out the window, and all of a sudden, whoom, this thing falls right by the window. According to my calculations, that bowling ball just fell by the window at 50 meters per second. Someone says, how do you know that? Oh, I just know that. 1 second later, boom, hits the ground. Sounds okay, how fast was it going when it hit? You couldn't see it then. Check and see if you're sitting next to somebody know the answer to a question like that. How many say 60 meters per second? Show of hands. My people, all right, that's right. Because every second go by is going to pick up 10 meters per second more than it had before. We're learning this stuff, huh? Let's suppose I said 1 second after that, what would it be? 7. See, it keeps picking up the same. Well, here it is right here. G is going to be 10. Let's just call it 10. If G is 10, just multiply by the number of seconds. Even if I told you it falls in 7 seconds, you can still do it. Maybe not 9 seconds. Okay, 9s are kind of tough, but say 7s, all right? 7s, you just say 7 times 10 is 70. How about I give a decimal? 7.9 seconds. Ooh. Remember the first time you saw 7.9? Oh, God. What's 7.9 seconds, gang? How fast it going? 79, whatever it is, okay? It's 7.9 to multiply by 10. Isn't that neat, huh? So that's the review, okay? Now, here's the more important question. Lee, question?
Yeah, so let's see. Last time we were talking about throwing a ball up in the air and then having it drop.
Yeah.
And so at the top, its velocity was 0. Or when you originally let it go, its velocity is 0.
That's right. Starts off at 0.
It started going down.
That's right.
You seem to have trouble with that.
That's right. Here it's 0 right here, Lee, okay? I drop it, now it picks up. Picks up, picks up, picks up, da, 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 da. And all we're saying is there's a relationship for how much it does pick up. It's simply G. And knowing how much it picks up then tells you how fast it's going. And that's just G multiplied by T. Is this too abstract, gang, when I say G and T and things like that and I've got alphabet? You know, some people like numbers, okay, but this is numbers, this is alphabet. Remember when you first get into that, you get into algebra, and you looked in the algebra book and there are no more numbers, all alphabet? You know, alphabet equations? Well, that's what this is. Does this turn anyone off? You can kind of see what we're talking about, can't you? When you take music, honey, you got to learn how to read the music first, yeah? Isn't that right there? Okay. Well, what we're doing is we're learning how to read the music of physics. The relationships, and we're just putting them in a musical way. Okay? How many people are tone deaf? Okay. I am a little bit. But anyway, that's what we're going to do here. Does that answer your question, Lee? So that's the speed we're going to pick up. Now I'm going to get to the part that's a little difficult for some people. That's how fast it goes. How far is it going to fall? Oh, some people get all mixed up. How fast, how far? How far is different than how fast, right? And how about it, gang? When I drop this thing, you're going to pick up distance, yes? You see it getting further and further apart, huh? What is the rule for how far it falls? Is there a rule? How many say, no, there's probably no rule for that. It's different every time. Come on, gang. What's the rule? You remember? Yeah. It was distance falling, d for distance, equals average out the g, t squared. And if g is going to be 10, and it will be for the planet Earth, then a half of 10 is 5. So we could just say 5t squared. So we should be able to find from here that that distance keeps getting greater and greater and greater the greater the time. That being true, you can answer this question. I take this bowling ball, I get up on top of a cliff, and I drop it. How far down is it underneath? 1 second later. Check the neighbor. How many say begins with an F, ends with an I? Yeah, it's 5 meters. 5 meters down. Okay? Remember that. Any object that falls from rest will fall a vertical distance of 5 meters in the first second of fall. If 2 seconds goes by, how far will it have fallen then? Even more. How much total? And how would you find it for 2 seconds, gang? You got your little rule right here. If 2 seconds goes by, you take 2 times 2 is 4 times 5, 20 meters. It will have fallen 20 meters. And let's suppose 10 seconds went by. You're in an airplane. You drop it from an airplane, it takes 10 seconds to hit the ground. See if you're sitting next to someone who knows how fast, not how fast, how far down the ground is. Well, 10 plus 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 10 or what? It's 100, honey. 100, okay? So now you got 100 times, it's going to be 500 meters down. So if you're ever falling off a cliff and it takes 10 seconds to hit the ground, your last thought will be, hey, I fell 500 meters. That's how far you'd go. Kind of see that? Any questions on all this?